So the first thing we do when we have our radar transfer plotting sheet and information for a one target plot is we have our ship's info, our course is 000 degrees, and our speed is 10 knots. We write this down on the bottom of the radar transfer plotting sheet to view later. Next step is to take the first range and bearing off of a target that you see. Our first range and bearing at 12 o'clock is 074.6 degrees at 10.3 nautical miles. We write this in any of the corners. I am choosing the top right corner for this target. When we measure with our triangles to get the correct bearing, we want to use that line on the bottom of the triangle to get the most accurate bearing reading. Once we use that line, we move our triangle up to the actual center line hash mark, aligning with that bearing taken. We count through our radar ring ranges to get an approximate location for a 10.3 nautical mile range. This is just an approximate line. We now want to open our dividers to measure 10.3. We are using the 12 nautical mile scale on this radar transfer plotting sheet, as the first range is only 10.3 nautical miles. If we used a different size scale, say a 3 or a 6 nautical mile range scale, the target simply would not be on the sheet. We technically could use a 24 nautical mile range, but then our triangle would be extremely small and hard to read. When we're using our dividers to get this measurement off of our range scale, we want to make sure we don't accidentally bump our dividers. If you have loose dividers, I suggest tightening them. My favorite type of dividers are the ones with the wheel in the center for the most accurate rating. We label that point R at 1200. And now we are just double checking our measurements. Our bearing looks good. Let's double check our range. I'm using a secondary pair of dividers without lead on them to make sure I don't add additional marks to the paper while double checking my measurement. Perfect. Next step is you are going to wait 6 minutes before you take your next range and bearing. For this plot, we are doing 6-minute intervals. For other plots, you might be doing any different kind of minute interval, whether it's 1 minute, 3 minutes, maybe 5. For this plot, we are doing 6 minutes. That makes a lot of the math extremely easy because 6 minutes is 1/10 of a mile. That's going back to the tenths rule. So as our range and bearing reads at 12:06, we have that target at 074.4 degrees at 8.9 nautical miles. I wrote that in that top right box, and I am double checking my bearing right now, making a slash mark around the 8.9 nautical mile area. Now taking my dividers with the lead in them to measure 8.9 on that 12 nautical mile scale. I always make sure that when I am using my dividers with lead in it to mark a range, that I do a little test mark on the actual scale on the left side as well to make sure I am actually getting an accurate reading and that my lead is going to be centered the same way on the scale as it will on the plot. Again, we are double checking our range and bearing. First with our bearing using that bottom line on the triangle, and next with the dividers without lead. And that matches up to the same bearing and distance that I originally measured. Now on to our next step. We are going to wait the same amount of time interval. So we waited 6 minutes between our first and second bearing and range. We are going to wait another 6 minutes before our third target plot. So I wrote it in the top right box. Our third range and bearing at 12:12 is 074.2 degrees and 7.5 nautical miles. Here I am measuring that bearing. Now you could easily see that I can slide my right-handed triangle up and down. Whenever you are moving triangles around, you do not want to accidentally bump them, and you want to make sure you have a firm grip on whichever triangle is your more stationary one, so that your moving triangle can freely move without getting its bearing off. Taking that range now of 7.5, marking it and labeling it. I'm labeling this spot M2 since it is the second M I am putting down. Again, always make sure you are double checking your work so that you can have the most accurate radar plot. Beautiful. Everything is double checked. Now we can actually connect the dots of those three ranges and bearings that we have taken to create our RML, our relative motion line. This is the line that ship travels across in relation to us. You can label that RML, and I like to do a little half arrow at the end. Now we can find some key information. First, we could find our CPA, which is our closest point of approach. You want to mark that line where it is perpendicular to your center hash mark on the radar transfer plotting sheet. You want to make sure that you add a little hash on the actual paper for a measurement we have to take in the future. I always write down CPA to actually mark that spot. We can take that measurement, and once we do find that measurement, I label that down as well on the radar transfer plotting sheet so that I don't lose that information too much. You can also put this information down just below that target range and bearing information on the top right-hand side. It has a little spot for CPA, for the nautical mile distance, and the bearing that it's at. The CPA I got for this plot was 0.2 nautical miles. I'm writing that down on the plot and up in that top right corner. Okay, now we actually want to create our triangle. So we're going to plot E. Since this is a 12-minute plot, and our vessel speed is 10 knots. We will use that to extrapolate the range we will plot E away from R. But first we want to plot our bearing. Now our ship's info, we are going 0, 0, 0. So we are going to plot the reciprocal of that from R, which is 180 degrees. So we just draw a line straight south from R, and then we could do our math calculation to get the distance. Using 60 D Street, again, 12-minute plot, and our vessel is going 10 knots. We have 10 knots times 12 minutes divided by 60. Now, when we divide by 60, that turns this measurement from minutes into hours. Our distance is 2 nautical miles. We are going to measure that from R down that 180 degree course line, which is again the reciprocal of our ship's course. And we can mark our E. We're almost so close to creating our triangle. We are now going to connect E to M. Now, we have plotted 2 different M's. Be sure to use the 12-minute M as we created a 12-minute E. You want to be extremely precise with E to M's line. And now we have our triangle. Be sure to remember the common phrases of we are, ER, as in our motion, and the other ship is E to M. E to M is them. That is the way their ship is truly moving, or their true motion. Their ship in relation to us, though, does travel along the relative motion line. So now we are going to start measuring E to M to find this target's true motion. When we do a measurement between E and M, we are able to find the speed. So we're going to measure that. We got 3 nautical miles. Now we can do our 60 D Street formula again. We have 60 times 3 nautical miles divided by 12. Now that 12 is because it's a 12-minute plot. This will equal our speed. Our target's true speed comes out to 15 knots. You can write that in the top right corner under Other Ships, Course and Speed. Write 15 knots for speed. Now we can measure the course between E to M to find that vessel's true course. So we use our triangle. Again, we're using that line inside our actual triangle. If you use the edge, you might be prone to errors. We connect the dots between E to M. We get our other triangle to move our main triangle down to the center. Again, using that center line of the triangle. I got 295.5 degrees true, but I realized that I kind of hit my triangle a little too much there, and I just want to double check one more time for the vessel's true motion course between E to M. So here I am just remeasuring that just to be sure. You can never be too sure with a radar plot. It's always great to continuously double check. So from that center peg of the radar transfer plotting sheet to the outside is my course of 295.5. I am putting that information again on that top right corner where it says other ship information. Now we are going to repeat both of those steps for the R to M line. Everything we just did for E to M, which is all of their true motion, we are now doing with R to M to find all of their relative motion. Again, when we do the measurement from R to M, we are going to use M2, which is a 12-minute plot. The distance I found between R and M2 is 2.8 nautical miles. Again, we use 60 D Street, 60 times 2.8 nautical miles over 12 minutes gives you your target's relative speed of 14 knots. There isn't an exact place to put this on the radar transfer plotting sheet, so I just put it below that target's information. And make sure to label it relative motion speed. Now we are again still measuring that R to M, but now we are finding the actual course between R to M. We want to line up that line on our triangles and then bring it down. Now I brought it down a little extra because I wasn't going to reach the left-hand side of that piece of paper by the way I started to move that triangle, so I did a double move. And again, we're looking at that line of the triangle, and I got 255 degrees true. Now I write that in the same spot, just below the top right corner, so that I don't lose that information. Now we have our target's true course and speed along with their relative course and speed. So again, from E to M is where they are actually pointing their true motion and the aspect of the vessel you will see, but they travel along the relative motion line in relation to us. Now we could start solving for TCPA, or time of closest point of approach. So we are starting to measure from R all the way to our CPA mark. The measurement I got for R to the CPA point is 10.32 nautical miles. We are going to use this distance again with 60 D Street. So with our 10.32 nautical miles, we are solving for this along this relative motion line. So we are going to use the relative motion speed that we found before of 14 knots. So we have 60 times 10.32 over 14, that will give us 44.2 minutes. Now we want to make sure we add that time to our R, so we'll get 1244.2. And you can put this information again on the top right of 1244.2. Now we are solving to see if we are in a crossing head-on or overtaking. I have my little boats. You can draw this on the paper as well. Since we are seeing the side view of this vessel there to the side of us, we are in a crossing situation. Since we are able to see their port side or their red side light, we are the give way vessel. If we were going to take action to avoid collision, we would turn to starboard and take their stern. We might even have to do a little bit of a speed decrease as well, as if we don't do anything, they will crash right into us. And that is everything you have to do to solve for a single target plot with no course or speed change.